in this video, oh, I forgot to label one of the edges. Let me look to see. This is an example from the book. 53. I think I only did one. 53. I could have just made up my own number, but I wanted to, if you're following along with the book, I want you to be able to see. Alright, so we're going to use Kruskal's algorithm. Hopefully I'm pronouncing that right. I don't know why it wouldn't be pronounced Kruskal, but I've never met the person, so I don't know if that's really how you pronounce it. Probably is. Alright, so Kruskal's algorithm is a way to, oh, I forgot another one. There's so many edges in this. It's easy to forget. Alright, so anyway, I guess it doesn't really matter as long as I realize that I forgot it. Might as well just leave the book up here in case I forget another one. 55. Did I forget another one? No, I did not. Don't really want the book up here because it's annoying. So we're going to use Kruskal's algorithm to find a minimum spanning tree in this weighted network. The reason for that is these numbers stand for something that's a cost. We want to minimize the cost. So if you look at Kruskal's algorithm, you might not be able to read it right there. You probably can. I wrote in cursive, but it's probably big enough for you to read. If not, you can read about it in the book. But if you look at it, and it even mentions it in the book, it's kind of like the cheapest link algorithm that we use to solve traveling salesperson problems. So what you do is you just look at your network and you look for the smallest number, and you're going to choose that. And you're going to keep doing that. You keep doing that one edge at a time. The only stipulation is you don't ever want to form a circuit. Okay, so let me see if I have a different color pen. I'm going to just draw lines like this to show you where the, or I might just erase the black line and redraw it with blue. I don't know, hopefully you'll be able to tell the difference. Maybe I should redraw it with red or orange. The problem with that is these markers don't show up that well. Plus this has black marker on it. I have every color. What about this one? Yeah, maybe I can do that. Alright, so I'm going to pick the cheapest edge. Do I see a 49, 45, 42? Make sure that that's the actual cheapest one. So 42, this edge right here, GF. And I'm going to actually write the number out here. So it's 42. See how that looks. Yeah, I guess you can tell the difference. Okay. Then I did see another 40, okay, 45 will be the next one. So I have to remember that that's 45. We haven't made a circuit yet, so that's good. You can choose this one too. That won't make a circuit. That was 49. Notice that it looks like there's a couple 51s. You can choose this 51, but you can't choose this 51. They probably did that for a reason. They're trying to show you, like, get to a point where the next one you can choose is either this one or this one. Now, if you have two edges that have the same weight and neither of them form a circuit, you can just pick whatever one you want. But here you can't, because you have to pick this one. This one would make a circuit. So you don't want to pick that one, so you want to pick this one. That's 51. Remember, we're trying to make a tree. So you can't have any circuits. So 53 is the next smallest one, and that doesn't make a circuit. Unlike the cheapest link algorithm, you can have more than two edges coming in to a vertex. You just can't make a circuit. That's the only stipulation. It looks like 55 would be the next, but that forms a circuit. 56 actually also forms a circuit. It would make this circuit here. 59, I think, is the next biggest one, and that does not make a circuit. You should also be checking to see if every vertex has been visited. You've actually been to A, G, D, B, C, and E, and F. So guess what? We're done. We made our minimum spanning tree. So to find what the weight of that tree would be, all you have to do is add up all these numbers. So that's 145 plus 53 plus 59 and 42. 11, 14, 19, 10, 19, 299. Okay, look at, we didn't have to use this, which was 74. We didn't have to use a lot of these big numbers. So we just made a minimum spanning tree that has a weight of 299. I want to see in the book if they actually figured it out and got 299. They probably did, because I just did it and got 299. Either that or they just didn't actually figure it out. Oh, yep, they got 299. Now, these numbers were millions of dollars, so whatever they did cost $299 million. But notice, the original network, if they had actually made, if they didn't make a tree and they added all these edges, it would cost like more than double that. So they saved probably over $300 million by making this minimum spanning tree. Alright, so if I do another video, it will be about maximum spanning trees, but I might not.